Hello and welcome to this video lecture. So in this video lecture, we'll start our discussion of differential equations. And as it turns out, probably one of the best points that was ever made to me when it came to differential equations was from my first Diff instructor, who pretty much said that with some exceptions, the solution to a differential equation is pretty much just found by guessing. Now, thankfully, it isn't quite that extreme. It turns out that there are some differential equations that lend themselves to particular approaches or particular conceptual frameworks that allow us to solve those differential equations in a relatively formal fashion. But for just any random differential equation that you can come up with, yeah, my original Diff instructor was probably correct. So understand that the differential equations that can be solved within these frameworks out of the infinite universe of all differential equations, it's relatively small. So with that said, what does that mean? That means that being able to understand the type of differential equation that you're working with is incredibly important, because once you understand the type, you'll be able to understand whether a formal framework exists for it or if it doesn't. So if you were always wondering why your Diff-EQ instructors were always like, this is this type of differential equation, right? They had about 7 different things describing that differential equation. Because if you knew those 7 things about that differential, and 7's a little bit of an exaggeration, but if you knew that many things about that differential equation, you'd be able to say, okay, this framework, this structure to solve it applies or it doesn't apply. And so understand that this whole idea of classifying and categorizing differential equations is absolutely crucial, because then we understand if a framework, sorry, can't talk right now, if a framework exists or if it doesn't. And so you need to pay careful attention to that. So I'm going to go ahead and start this discussion off with exactly that. Let's go ahead and start talking about ways of classifying differential equations. And then, of course, in subsequent lectures, we'll talk about different ways we can solve some of those differential equations. So differential equations, of course, are equations that involve combinations of functions and or their derivatives. So specifically, let's start with one of the most important classifications. So if derivatives are taken with respect to, and here that's generally abbreviated as WRT, so I may use that in the future. So if the derivatives are taken with respect to one variable, then the equation, and here I'll shorten down equation, the equation is called an ordinary differential equation. Oops. And here we will kind of refer to those in a shorthand Diffie-Q. And when we're talking about an ordinary differential equation, we can say that that's an ODE. Again, ordinary differential equation. So examples of some ordinary differential equations: md squared x dt squared plus b, or in some cases c, dx dt plus kx is equal to f of t. That would be an ordinary differential equation because we have, let's go to a different color. We have the function itself, and we also have its derivatives. Notice, though, no x's over here. That's just, those are t's over on that side. So that would be an ordinary differential equation. Another one could be sine t dx dt plus dy dt equals 0. So of course here we're taking the derivative with respect to time. So we only have the derivative with respect to one variable, and so of course this would also be an ODE. In this case, because we're taking derivatives with respect to time. We can also take the derivatives with respect to multiple variables, in which case this particular expression would be called, so here I'll shorten down equation again, is called a partial, because we're using partial derivatives, a partial differential equation. And so these are abbreviated as PDEs. And as some examples for PDEs, we can have partial squared of phi with respect to x squared, plus, where of course this notation where we're using the squareds really represents a second order derivative. And then we can have the same thing with phi, but now with respect to y. So obviously we're taking the derivative with respect to two different parameters. Here we're dealing with spatial parameters, x and y. And if you are familiar with fluid mechanics, you will recognize this partial differential equation as the two-dimensional potential flow equation. But clearly it's a partial differential equation because we're taking the derivative of phi with respect to both x and y. So another one, how about u du dx plus v dv dy is equal to 3x plus y. And so here, since we're taking the derivative again with respect to both x and y, that would be a partial differential equation. Now, as you've seen, and so this one, though, the second example just deals with the first derivatives. So we can see that another important property of a differential equation is the order. So the order of the equation is just the order of the highest derivative in the equation. So fairly simple one, 5 dx d, no, not dx dx, dx dt plus 3x is equal to 2t. And so, of course, this would be a first order differential equation because the highest derivative is a first order differential. 2d squared x dt squared plus x dx dt plus x is equal to 0. That would be a second order, looks like a very unpleasant second order, differential equation. These, of course, are all ODEs, so let's go ahead and get a PDE in here. So how about du dx plus dv dy equals 0? Well, those are both first order derivatives, and so this would be a first order differential equation, but a partial differential equation. Now, again, if you're familiar with fluid mechanics, you might recognize that as the second order incompressible continuity equation. So that's kind of another fun one in there. And if you haven't had fluid mechanics yet, you can maybe start to appreciate that fluid mechanics has all sorts of fun math associated with it. For another one, let's have 3y times partial of u with respect to x plus partial squared v with respect to y squared is equal to x. And of course, this one is going to be a second order PDE. So we can see that depending on the highest order of the derivative, that will drive the order of the differential equation. Another classification is that the equation is called linear, and we'll discuss more about what linear means in just a moment, is called linear if one the function and its derivatives are raised to the first power. So in other words, we can't have square roots of derivatives. We can't have derivative squared. We can't have sine of a derivative. So none of those would work for a linear differential equation. And we'll see why we're interested in linear differential equations a little bit later. Secondly, and one other thing we can't have is we can't have, and I'll get this in a moment, but it kind of relates to this idea of first power. We also can't have instances of the function multiplying itself. So in other words, this right here would completely wipe out that particular differential equation from being a linear differential equation because we have x times dx dt. So that wouldn't work out. And the coefficients, so here we can capture that, and the coefficients are a function of the independent variable only. So you can see then how this second requirement effectively, if we interpret two things that are multiplied together, s being one being a coefficient, the other one being a function, we can see that that second description rules this one out, because here the coefficient, i.e. the x, if we want to choose that as the coefficient, clearly isn't a function of the independent variable only. So that would, of course, mean that that particular differential equation is nonlinear. Now, what that means is that these particular equations have a specific form. So this equation, or a linear equation, can be written in the following form. ANX, and here I'll go to our standard math notation to be more consistent with the text. dn of f dxn plus an minus 1x dn minus 1f of f. You got a little funky there, sorry about that. dx n minus 1 plus, and then this just goes all the way on down, dot, 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 so we'll just do it that way, dot, 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 plus a1 of x df dx plus a naught of x times f is equal to potentially g of x. Where, again, these coefficients can be functions of the independent variable x, or we could say that they are constant, which, again, for a constant, understand, here I'll erase this in a second, understand a constant is what? A constant is just some constant times x to the 0. So we can argue, oh, hey, yeah, you know, a constant is a function of x, it's just x raised to the 0 power. So that gives us a little bit of a better understanding of, for some reason my eraser seems to be broken right now. There we go. I have no idea why that's doing what it's doing, but that's okay. We got it all erased anyway. So examples of, so again, getting back to this, so yeah, we can always write a linear differential equation in this form. Now understand that just because we have a linear differential equation doesn't necessarily mean it's a relatively easy one to solve, but there are certain properties associated with a linear differential equation, and we can then we can understand those properties, and then that gives us a better understanding of how to work with that linear differential equation. So now you're starting to see that I'm getting into this idea. So I initially indicated that we're interested in categorizing differential equations because of frameworks, but now I'm bringing in this understanding of the property of the differential, or the properties of the differential equation, where one of the properties is the framework that allows us to solve that differential equation. So again, not only can we get some really important information about how to solve a differential equation by being able to understand what that differential equation is, we are also able to then understand other properties associated with the differential equation. So differential equations with non-constant coefficients can sometimes be quite challenging to solve, but nonetheless, they will still be linear if we can shoehorn them into this particular form. So let's see some of those particular forms. So as some examples, so we have e to the t times d squared x dt squared plus sine t dx dt plus 3x is equal to t. That would be a linear differential equation because the coefficients, albeit two of them are non-constant, the third one is constant. they're all functions of the independent variable. And then we have the function and its derivatives raised to nothing but the first power, and they aren't part of transcendental functions or anything else. And then, of course, any functions on the other side or any values on the other side involve only the independent variable itself. And so another example, and one that you might start to recognize has other classifications attached to it. And here I'll just allude to those now, and we'll discuss them a little bit later. 4 dy dt plus 5y is equal to 0. This one, we have constant coefficients, where again, 4 could be viewed to be equal to 4x times t to the 0, and 5 can be equal to 5 times t to the 0, right? Why not? And so we can see that those are functions of the independent variable, only just, as we might call it, degenerate functions, because the t doesn't need to be expressly written for those particular coefficients. And then, of course, those coefficients are multiplying. Sorry, let me get my pen back up. Are multiplying. Wow, don't know why my pen's having trouble coming up. My apologies. Are multiplying instances of the function. And by instances, I mean the function itself or its derivatives. And so we can see that these are examples of linear differential equations. And if the differential equation isn't linear, then in relatively straightforward fashion, that differential equation, and so what I mean by, again, linear versus now what we will call nonlinear, is that a linear differential equation can be expressed in the form indicated, and if not, then it is called nonlinear. So we've already seen some nonlinear differential equations, but let's go ahead and take a look at a couple others. And some of those nonlinear ones were up here. This was a nonlinear differential equation, clearly. So another form of a nonlinear differential equation for dy dt plus 5y squared is equal to 0. And clearly we fail because y is not raised to the first power. And another one would be y dy dt. So echoing the one that we had above, times 5y is equal to 3t. So here we're multiplying the function and its derivative together, so clearly that would make it nonlinear. Now, if this y, though, was a t, however, then this would again become a linear differential equation. But in this particular case, because we have y as the coefficient for the first derivative, then this is clearly a nonlinear ODE. Let's talk a little bit more about being linear. And we're going to see an interesting, I don't want to say consequence, but an interesting property associated with the definition of a linear differential equation. So when we talk about a linear behavior, and here let's just go ahead and talk about a linear function, though we can talk about linear behaviors of other things beyond functions. But for right now, such as a linear operator. But right now, let's just go ahead and work with a function, because this idea of being linear, whether it's a function, whether it's an operator, etc., they all spring from the same place. So for a linear function, we would have that f of y1 plus y2 is equal to f of y1 plus f of y2. Now, saying that in math is, you know, it's like, oh, what's the difference already? But actually there is a very distinct difference here. And that's what I want to cover. So let's cover that in words, because what is this saying? This is saying that we can, for a linear function, we can either operate on the combination of whatever inputs we have. In this case, we can combine y1 and y2 together and then have the function operate on it. Or we can have the function, if it's a linear function, we can have the function operate on y1 by itself and then y2 by itself. And then we sum up the results of the function operating on those two inputs, but operating on them individually, and we end up in the same place, right? That's where the equal sign comes into play. We end up in exactly the same place, whether we operate on them individually or we operate on them all at once, all together, which is generally more complex. And so that's the beautiful thing about this idea of a linear function or a linear property, is that we can choose to operate on things individually, which is generally a lot easier, and then combine together those results from operating on them individually, and we end up in the same spot as if we operate on things all together. If you've taken mechanics of materials, you kind of already know how this works. Because maybe I have a beam and I'm trying to figure out the beam bending associated with, and for good measure, let's throw in a moment and let's put in another point force. And then if you have a really mean instructor like me, then we have a distributed moment over here. And we could just keep piling on more and more things. And in mechanics of materials, there are ways where you can handle all of these inputs together, though they are relatively ugly, such as you divvy these guys up into the beam up into different segments, looking at what's happening at all these different segments. And then you pass off boundary conditions from one segment to the other segment, and it's through the boundary conditions that the segments are talking to each other. That's this end of understanding what's happening with linearity, where you aren't separating these out. You're looking at them all together, and then you're marching down the beam, integrating their individual effects. And that can be, and generally is, quite painful. So instead, another thing that you can do is you can look at what is happening with this distributed load by itself. Oh, come on, Ben, be good. You can look at what's happening with this distributed load. You can look at what's happening with this moment. You can look at what's happening with this point load. You can look at what's happening with this distributed moment, each one individually. So you can break this up into 4 different cases. And figure out what's happening with the deflection of each of these individual cases. Kind of got a little bit off there, my apologies, but really the most important thing is you get the idea. And then what do? You figure out the deflection for each one of these, and then you just add them together. And that was called the method of superposition. And so you're already familiar with this idea of either looking at everything that's happening all at once, which is generally quite complex and difficult to deal with, or you can look at everything individually, figure out what's happening with each of these individual ones, which allows you to build a library, if you want to call it that way, or an alphabet of different load cases. And then you just figure out what's happening with each elemental load case, and you add up the results, and you're in the same spot. You end up in, finding exactly the same deflection, except this is generally a whole lot easier. One assumption, though, with the method of superposition is that the beam was in the elastic range, meaning that you had a linear relationship between stress and strain. So this idea of linear behavior was actually built into this idea of superposition. And that's effectively why understanding whether or not we're dealing with something that's linear is so crucial, because when we are dealing with something that is linear, we can go ahead and use superposition. We can look at the elemental cases individually and then just sum up what's happening to figure out what's going on with the overall case. So it makes things considerably easier. Okay, so with that, let's go ahead and see if I can get my eraser working here. Okay, for some reason the eraser is way, way, way slow. I apologize, don't know why. But I think I'll get rid of most of this. Come on, be good. There we go. Okay, so with that said, hopefully you can, I guess we can get rid of the beam altogether. So if you've been exposed to this idea of superposition, or the method of superposition in strength of materials, or just superposition generally, that's exactly what this idea of dealing with a linear system, or in our case, a linear function, is all about. You can either work with the different inputs individually and then combine together the results, or you can work with everything, all the inputs all together, combined all together, and then that's the same as dividing them out. Though generally, as I already indicated, working with all the inputs all at once, all together, is generally much more difficult than working with them individually. Another thing, another property associated, or another property that has to, a linear function has to have, is if you scale the input and then operate on that with the function, you can just go ahead and operate on the input with the function, or using the function itself, and then just scale the output. The two are the same. So again, that means that if you double the input, you double the output. You cut the input in half, the output gets cut in half. That's what that's saying in words. So when we look at what these properties mean now for differential equations. And let's actually move that indentation out a little bit. Again, I don't know why the eraser's so slow today, and I apologize for that. So when we're looking at differential equations, let's see what that tells us. So let's say that we have the following differential equation. dy dt plus 5y is equal to 0. And now let's say that we have a combination of two y's coming in. So if we have for dy1 plus y2, so we'll have a combination of two inputs coming in, y1 and y2. So when we take 4 dy1 plus y2 and we take the derivative of it with respect to time, plus 5 y1 plus y2, we want to know, is this equal to, so we'll put a little question mark there, is this equal to f of dy1 dt plus 5 dy1 plus then 4 dy2 dt, and I'll move this over just a hair, plus 5 y2. So that's what we need to show. We need to see, do we end up with this? And if we do, then we at least satisfy one of the requirements for dealing with a linear, in this case, system, since we aren't necessarily dealing with a function. So let's go ahead then and work on the left-hand side a little bit. And we know from derivatives that we can go ahead and quote unquote distribute the derivative out. dy1 dt plus dy2 dt plus, and then we can distribute out the 5 y1 plus 5 y2, and of course we haven't changed the right-hand side. Now going ahead and distributing out the 4, and you can see that everything's going to work out well here. dy2 dt plus 5y1 plus 5y2. And we're still wondering if it's equal to the right-hand side that I wrote up there initially. And of course, just rearranging the terms, we get 4 dy1 dt plus 5 y1 plus 4 dy2 dt plus 5 y2. And that is clearly equal to, so we'll put a little check mark here, our original right-hand side, which you can see is exactly the same thing. y1 here, the y1's there, separated out, the y2's there, separated out. And so sure enough, this would indicate that we have satisfied the first requirements associated with being a linear system. Now, of course, if I had a constant alpha, if we wanted to do the second check, which would be really, really simple because I could just substitute in an alpha there, I could substitute in an alpha here, and then we would have to make sure that that is equal to 4 alpha dy dt plus alpha 5y, or in other words, we could just factor out the alpha, 4 dy dt plus 5y, where again, that alpha is a constant, it's just a scalar. And so, of course, what do we know? If I multiply y by a scalar alpha and then take the derivative, that scalar just comes right on through, and sure enough, this is exactly what we would get. So we can see then that sure enough, as per the definition, this is a linear differential equation. Let's go ahead though. And of course that isn't a proof, but well, actually what I just went through was sufficient to be a proof for the alpha. So this isn't a proof that all differential equations with this form up here. So I'm not trying to prove it, just trying to show you a couple cases. So I'm not proving this, but you can see that at least it's standing up for a couple different cases. Holding true, let's say it that way, for a couple different cases. So we have 4 dy dt plus 5y squared is equal to 0. Well, let's go ahead and do exactly the same thing. So we need to show that 4 dy1 plus y2 over dt plus 5 y1 plus y2 squared is equal to exactly the same thing. Except now understand that the y's themselves, not the derivatives, the y's themselves are squared. So we need a y1 squared plus 4 dy2 dt plus 5y2 squared. And so, I mean, kind of looking good so far. Of course, the first one is going to break into 4 dy1 dt, just like it did up above, plus 4 dy2 dt. And so everything's looking good until we realize, ooh, wait. When we square something with parentheses around it, what do we have to do? We have to distribute things in a very specific way, and we end up with a 5, sure enough, a y1 squared, which is great, plus a y2 squared, which is great, but the problem comes in with the 2y1, y2. So we'll still keep the question mark, is that equal to the right-hand side? But I think you can see, and let's just work it out in its gory detail. dy2 dt plus 4 dy2 over dt plus 5y1 squared plus, oh, nope, 10. We need a 10 there. y1, y2 plus 5y2 squared. And we want to know if that's equal to the right-hand side. And then we can, of course, say, okay, this is wonderful. dy1 dt plus 5y1 squared. Yep, looking really good. And then we have a plus 4 dy2 dt plus 5y2 squared. Everything looking great until we realize, nope, we can't get rid of that 10 y1, y2, y1 times y2. And so that doesn't work out, which is exactly what the definition of a linear differential equation indicated. If we have a y squared, clearly that's not going to work out. That's not going to be a linear differential equation, and we can clearly see that that's the case here. Now, this is, of course, taking y and breaking it up into two other functions, y1 and y2. So that's clearly going to be, so when we have a y squared, that's clearly going to be an issue, or even if we have an issue, a derivative squared in this particular case, that's clearly going to be an issue with the equation, the differential equation being a linear differential equation. And so then we're going to have to work with that particular nonlinear differential equation in a different way than we would be able to work with a linear differential equation. And as it turns out, nonlinear differential equations are generally considered much more difficult to work with than linear differential equations. And so that's one of the reasons that we are very interested. We are very interested in understanding whether or not the differential equation is linear. So then the question is, and hopefully I've already helped answer it, so let's get it in your notes. So the question is, why do we care? And so when we deal with a linear system, clearly then we can say that the overall output is just the sum of the individual output components, i.e. one from each input. Oops. There we go. Created by, again, the individual input components, or individual inputs if we choose. And so this, of course, is the key to the method of superposition. And of course, as I already indicated, when we have a nonlinear differential equation, that's not the case. So if maybe the beam is going into the plastic regime and we don't have this linear relationship between stress and strain anymore, the output cannot be simply the sum of the output components for a nonlinear system. Now, so that's why being able to identify a linear system is so crucial, because if we look at it in the real world, what does that mean? That means that I can go ahead and excite the system with some fundamental inputs, some very well-known inputs, and if I can then look at my input signal as a combination of some of those simple input signals, then I can just say the overall output will simply be whatever the output was for each of those individual simple signals summed together. And that will be the output for the more complicated signal that was a sum of those individual input signals or simpler input signals. So that gives us an understanding of why we would be interested in this idea of whether or not we're dealing with a linear system, even from an experimental perspective. Because of course that's exactly what you do in an experiment. Here's our system, let's give it a bunch of simple inputs, let's see what it does. Okay, now for a more complicated input, that's a sum of some of the individual inputs, we would expect to see that sum at the output. And if we go ahead and input that more complicated or more complex signal and we don't see that sum coming out, what does it mean? It means that we're dealing with a nonlinear system. And you could determine that right then and there experimentally. So it's pretty interesting how this plays into our understanding of even how we would test something experimentally. So one thing that I do want to note, though, is that if the differential equation is not equal to 0, i.e. you'll recognize that as being non-homogeneous. So if it is non-homogeneous, strictly speaking, we aren't dealing with a linear differential equation. So if the differential equation is not equal to 0, from our understanding of what a linear differential, or sorry, what a linear property is, let's just say it that way, when something is linear, strictly speaking, that's nonlinear. So even though we will call the differential equation a linear differential equation, even when it is not homogeneous, right? This is indicating that it may not be homogeneous. And so we'll still call it a linear differential equation. Understand that it really is only linear when it is equal to 0. When the equation is said, the equation in this form, let me be a little bit more precise, when the equation in this form is equal to 0, i.e. when it is homogeneous, if you kind of remember that particular term. So here I'll try not to put in homogeneous because I haven't introduced homogeneous yet, but strictly speaking, if a differential equation is not equal to 0, it is nonlinear. And so to see that, let's say that we have a linear ODE that is dealing with a function f. Well, here, let's just do f. Oh, erase, erase, erase. There we are. And that linear ODE, so whatever's on the left side, so that's going to be our linear ODE, is equal to 0. So it's now homogeneous, if you remember that term. And so let's say that we have two solutions. Let's say that this yields two solutions. F1 and F2. Well, if they are solutions, that means that when we go ahead and take all the derivatives and multiply by all the stuff on the left-hand side for F1, when we do that, we get everything equal to 0. Because the left-hand side, once I do all the operations, the left-hand side has to equal the right-hand side. And the same thing with, oopsie, sorry, got a little rambunctious with my parentheses. Same thing with F2, right? So, don't know why my pen's having trouble. I'm pretty sure I selected it. There we go. For some reason, it's just really slow today. So same thing for F2, right? So if F2 is a solution, that means that if I plug in F2 for F, and I take all the appropriate derivatives, whatever the function F2 happens to be, I take all the derivatives, multiply, add, do whatever I have to do, then that has to be equal to 0 as well for this linear ODE. So then my linear ODE for F1 plus F2. Well, remember, this is a linear ODE, so that allows us to say that and we'll discuss this in more detail later in the term. So that means that if it's a linear ODE, I can, of course, just operate on F1. I can take the derivatives and add and multiply and do everything else I need to for F1 by itself, and then I can do the same thing for F2 by itself, and then I can add the two together. And clearly, what do we end up with? Well, we already established that these are solutions. We define them to be solutions. And so this guy is 0, this guy is 0, and 0 plus 0 is 0, and sure enough, there we go. The combination of these two functions, when operated on or substituted into our linear ODE, will give us a solution, just like each individual one would give us a solution. It turns out that it could also be, of course, a linear combination, but we'll discuss that more in the future. Now, if, on the other hand, let's say that our linear ODE is non-homogeneous. Let's just make it equal to a constant. And let's say that we again have two solutions. Clearly, these solutions would probably be different, however, but we'll still say that F1 and F2 are both solutions. And so you can see exactly what's happening. Linear ODE. So if I go ahead and substitute in F1, that's a combination of a parenthesis and an F. F1. Clearly, what do we get? We get K if it's a solution, right? We also have F2, which is equal to K. But then if I substitute in the two added together, so we would still call this a linear ordinary differential equation. But you can immediately see that it doesn't strictly, so even though we would call this a linear ordinary differential equation, it doesn't strictly meet the requirements and the properties of being linear. Because, of course, here I can write out ln ODE F1 plus ln ODE F2. This one is equal to K. This one is equal to K. What's our output? 2K, whereas the original ordinary differential equation had K. And so the linear combination of the two will not give us the answer. Well, I shouldn't say linear combination. The sum of the two solutions will not give us the answer, the proper answer, when we substitute that sum back into the linear ODE, the linear ordinary differential equation, even though we would call it linear. So really the key here is to understand that this idea of linear, when we're talking about an ordinary differential equation, really only applies to the homogeneous case. It doesn't apply to the non-homogeneous cases. And so what we can do is we can find solutions for the homogeneous case where it's set equal to 0. We can find solutions for the homogeneous case And then for those homogeneous solutions, we can substitute those back into the differential equation, as it turns out, and everything works out just fine. We can substitute in the individual solutions, we can substitute in combinations, the sum of the solutions, and we can even substitute in sums of the solutions of those homogeneous solutions scaled by whatever scalar we want, as it turns out. Again, we'll discuss that more, but it's important to recognize that, strictly speaking, only when you're dealing with a homogeneous linear ODE do we truly get that property of linearity coming on through. And when it's non-homogeneous, when it's not equal to zero, then all of a sudden we start running into problems, because that's not actually, as it turns out, that's not strictly a non-homogeneous differential equation is in the strictest terms nonlinear. So with that said, I've talked about homogeneous quite a bit, so let's go ahead and get that defined. So a linear ODE is called homogeneous if, when all instances of the functions are moved to one side of the equation. Here, I'll avoid writing that. The other side is zero. And so then we will call it a homogeneous differential equation. On the other hand, of course, and here I'll refer back up to that other side, is not zero, then the equation is non-homogeneous. And even though we have these kind of arcane mathematical terms, homogeneous, non-homogeneous, it turns out that from an engineering perspective, dealing with a non-homogeneous differential equation has a very straightforward meaning. And what we'll see is it means that we're just sitting there pushing on the system. So it'll take us a little bit to get there, but understand that when we're talking about a non-homogeneous differential equation, it just means we're exciting the system in some way by giving it some kind of input. And that's all that means. Whereas a homogeneous differential equation, and we'll kind of poke at this a little bit, but a homogeneous differential equation, the only way to get that thing going is to have the system not at its equilibrium position at some point in time, and then letting it go, and generally that point in time would be zero, and then letting it go and then seeing what the system does. But that's the only way to get a homogeneous equation or a homogeneous system doing anything, is to give it what we would normally call non-zero initial conditions. So understand that For us, when we look at these non-homogeneous differential equations, we still have to recognize that they are not strictly linear, but we also have to recognize, well, that's how we operate as engineers, is we usually give systems inputs. We usually excite them in some way, and that would, of course, that would yield a non-homogeneous differential equation. Let's get into a special case of linear differential equations. So here we'll cover both cases. So a linear system can have coefficients. That are clearly a function, as indicated before, a function of the independent variable. Here I'll say explicitly or they can be constant, which again, as I already argued, can be viewed as still a function of the independent variable, just the independent variable is raised to the 0 power, which would mean that it's 1. So here we'll just say that since we wouldn't have to write the independent variable in that particular case, we'll just call that a constant coefficient. And that particular term, or that particular type of linear differential equation, is called linear time invariant. Otherwise known as LTI. And LTI systems are systems that we deal with all the time in engineering. And one thing I do want to mention, have it in my notes, it's important to recognize these are the coefficients. So the coefficients are constant. Clearly not necessarily the system response. And I'll abbreviate system response quite frequently in that way. So what do we mean by a time invariant system, a linear time invariant system? Well, the linear is obviously coming from the definition of a linear differential equation. So what does the time invariant mean? It means that the system itself, regardless of excitation, regardless of what time it is, will have exactly the same properties. So as an example, if I am pulling on a wagon, and maybe that wagon is full of sand, I'm pulling on that wagon would be in some ways represented by an LTI system, because nothing's changing in that wagon in time. I'm just pulling on it. However, if there is a hole in the bottom of that wagon and we have sand that is draining or falling from that wagon, that means that the wagon's mass is changing in time. And so at that point in time, I wouldn't be able to deal with my coefficients in the differential equation wouldn't be constant. I wouldn't be able to necessarily deal with that particular wagon's, the mathematical description for that particular wagon using an LTI differential equation. Whereas in the first case, where the sand was just sitting there in the wagon and wasn't moving, wasn't changing, just sitting there, that would be an LTI. And so another example, though a little bit more extreme, is of course a rocket. So rockets can't be generally considered linear time invariant systems, right? Because just like the wagon where the sand is falling out, what's a rocket doing? It's just dumping boatloads of propellant out the back end of the rocket, and so the propellant had to come from somewhere. It came from within the rocket, and so that means that the rocket's mass is changing, generally changing quite dramatically over time. And so looking at that rocket at t equals 0, or our wagon with the hole in the bottom at t equals 0 versus t equals 5 minutes later, we got a completely different wagon, a completely different rocket, because the masses are different. And so we would have to capture that in the differential equation, and that would show up in the coefficients associated with the differential equation. Turns out much harder to deal with coefficients where the time, in some cases we can get away with it. We can actually figure it out relatively easily, but in a lot of cases it is very difficult to deal with time varying systems. And so if we can identify that we're dealing with a linear differential equation that is time invariant, we will usually have a much easier time analyzing that kind of system than we would if things are changing in time. And that is true to such an extent that in some cases people will actually analyze, even though they have a time varying system, they'll analyze the differential equation over such a short period of time that they can consider the system to be time invariant over that short period of time for their differential equation. And then they don't have to work, and they can solve the differential equation, figure out what's going on before the system changes to such an extent that their analysis is no longer valid. So you can do that as well and kind of break the analysis up into, smaller chunks and try to get away with it that way. But you have to be a little careful with that. So with that, hopefully you can start to see the different classifications that are associated with differential equations. And even more importantly, hopefully you now have a better understanding of why we're interested in classifying them. It's not just for the sake of sounding really smart by saying, oh, hey, that's a that's a linear time invariant homogeneous differential equation, right? You sound so sophisticated saying that, but really the reason for it is because, again, in some cases we have mathematical frameworks, mathematical approaches to solving those differential equations. If we can properly identify that differential equation as one that can be properly solved by that particular approach, and if it's something different, we can't use that approach. And so it kind of tells us, okay, we have from a mechanical perspective, we have a fastener. The fastener has a nut on it. What do we need to do? We need to pull out a wrench to take the nut off. On the other hand, if we just have a screw going into a blind hole, we're going to need a screwdriver. And so by identifying what's going on with the fastener, we know which tool to pull out, either a wrench or a screwdriver. Same thing here. Once we can identify whether we're dealing with an LTI differential equation, linear time invariant, we can go to one mathematical framework. If we identify that we're dealing with something else, we have to go to a different mathematical framework. And so that's the whole key with this idea of identifying the differential equations, so that we can then pull out the right mathematical tool. Again, kind of thinking back to the mechanical analogy, the right mathematical tool to help us solve that particular problem. So with that, we will call this video lecture a wrap.